Okay, can you hear me? Hello? Is the screen also visible?
Yes, sir.
To cover is alternating currents in this series on electromagnetism, right? So we'll start with alternating currents today, and let's see how far we can cover it today. Okay, so far you have been dealing with direct currents, right? And direct currents are the direct currents. What is a direct current? If I plot a graph between current and time, so as time moves forward, the current remains constant. It does not change throughout the entire cycle, right? So we have a constant value of current. Suppose that this is I naught. Another type of current is alternating current. Which if I plot it, it looks like a sinusoidal wave, right? Which means it alternates between positive and negative values, right? So the cycle looks like this curve. It can be a sine wave, it can be a cos wave as well, right? So this current vibrates back forward, goes backwards, again moves forward, and then again starts going backwards. So it has two directions which are specified with a positive signature, and the other direction is specified via negative signature. Now, so far, when we were dealing with direct currents, our potential difference would be just a constant value, right? Just some V, and similarly, I would also be some constant current through the circuit. In alternating current, this value changes as time progresses forward, and it changes as a sine or a cosine function, right? We know that a cosine function is just a sine function with a phase added to it, right? And similarly, same goes for a sine function. It is a cosine function with some phase again added to it. So for an alternating current, we have an equation that looks like y is equal to a sine, let's give it another constant, b x plus c. Now, what is this a? This a specifies the amplitude of this wave, right? You must be familiar with this from your course on or your chapter on, what was it, oscillations, right? And b specifies the frequency of the oscillation or number of cycles in 2 pi radians. So let me write this down. This is the amplitude, and this b specifies number of cycles in 2 pi radians or 360 degrees, right? And c is the y-intercept, right? Y-intercept as in where this curve crosses this vertical axis. In this case, in this graph that I have drawn, it's 0, but in general, it will be a non-zero value. It's also referred to as the mean value of whatever is on the y-axis. So using this equation, we can write down an equation for the current and voltages, right? So the current which is not going to be a constant anymore, it's going to be a changing current, would be I is equal to I naught. Again, what is this I naught? It is the amplitude of the current, the maximum current that I can have, times sine omega naught, where omega naught is that frequency of the oscillation, times time. Now in this equation, you can put any value for time, and this will give you the value of current at that particular instant. And because we know from Ohm's law, V is equal to I times R, right? Or that the voltage is directly proportional to the current in the system. R is just a constant. It's a constant of proportionality, or you can just refer to it as a constant. So from that, it should be clear that voltage will also follow the same form of expression as current does, right? Because R is just a number. It's a constant number being multiplied. So it's just scaling the potential, right? So V naught sine omega naught times t. This is the equation. These are the equations for current and voltages for an alternating current. This value, this thing that we call I naught, or the amplitude, is also sometimes referred to as the peak current. And again, the name specifies what it means. It is the maximum current during the entire cycle. Any questions so far?
No, sir. Sir, what's X, Bx?
Oh, X is the variable that is plotted on the horizontal axis, right? So in our case, when we're discussing alternating current, X is time, right? X is time. Y can be current or voltage, right? Depending on what physical quantity that you're talking about. If you're talking about current, then Y is current and A is the corresponding amplitude of that current. And if Y is voltage, then A is the corresponding amplitude of that voltage, V naught. And X is just the variable that's changing. So you can change time. At 0 seconds, what's the current? At 1 second, what's the current? At 2, what's the current? So the current will keep on changing. And that's what alternating current is, with an additional factor that it goes forward and backwards as well. So, yeah. Anything else?
No, sir.
So now there is a concept that's called root mean square. Now this concept is applied to both voltages and current. So let me again draw this graph. So this is my voltage and this is my time. Suppose that I have a sine function, something like this, right? And it continues on. So ignore my drawing. It's not the best, but it does the job. So this would be some value V naught, right? Would you agree with the fact when I say that this would be the peak voltage of this graph?
Yes.
Okay. And corresponding to that, there is minus V naught on the opposite side. This is one cycle, so that's the time period of the oscillation. if I want the mean voltage, mean as in average voltage, so we can use V and put a bar on top of it. That means mean voltage, or V mean. How would you compute that in this graph? Just how you do it simply in statistics, right? You would just add the two voltages and divide it by 2, because there are two voltages. Okay, what should you expect before I do that? What do you expect you should get for mean voltage by looking at the graph itself? Any idea? Just take a guess. Give me any number.
0.
Sorry?
0.
0, right? And can you suggest why? Why did you say
Because
0?
the positive and negative values would cancel out, and that would be 0. So
Yeah,
0
exactly.
divided
So
by t
the
is
maximum, yes. So exactly, the maximum and the minimum voltages are same but opposite in signature. So that means that the average will be just 0. Or just by looking at the graph, whatever I have up, I have exactly the same as down, and in the middle there is just nothing, 0. So the average should be, so it's V naught plus minus V naught divided by 2, which is just 0. Okay, so that's something that's not giving you any information really. It's just saying that, okay, the mean voltage of such a system is 0, or it vanishes. What if I take this same graph and I square it? So I have T over here and V over here. Now I square it, so this would be V squared. How should the graph look like? What would you expect? Whatever curves we have upwards will increase in length, or their amplitude would increase. What I have down, I cannot go down, because we know that a square of some number is always greater than 0. It can be equal to 0 as well if voltage is 0, but it's greater. It's a positive number. It's not going to be a negative number. So instead of going down, the graph goes again back up. And it looks something like this. So all the cycles will just continue in exactly the same fashion. So it keeps on moving like this. Now here, there's some new value, V naught squared, as the peak voltage in this case. Now in this case, we calculate mean square voltage. So this should clear up what mean square voltage means, right? Initially, before, we just computed simple mean of voltage versus time graph, where we had up and down cycles. In this case, we have only positive values. So we compute the mean square of voltage. And what would that be? That would just be 0 is the minimum value, maximum value is V naught square. So V naught square plus 0 divided by 2. This mean square voltage is also referred to as the root mean square. The mean square ms, Vms, and this is equal to V naught square by 2. Now, usually, be in your questions, you would be given this thing, that there is some root mean square value of voltages or currents. Root mean square of voltages or current, right? What would that be? that would just be taking the square root of the mean square voltage, which is just V naught by under root 2. Any questions so far? Is it
No,
clear?
sir.
Is the concept of a root mean square voltage clear?
Yes.
Okay. All right. Okay, so what does it mean for, I mean, okay, root mean square, we can compute that, well and good. But what does it mean for, to say root mean square of voltage or current? Before I get to that, would the equation be exactly the same for current as well, for root mean square, just replacing V naught with I naught? Would it be the same?
Yes.
Yes, it would be the same, right? Again, because V is related to the current with I times R, where R is just a constant. So the whatever shape V has is the same shape that I will have. R is just a number that scales the potential drop across it. So, which means that the for current, which is I r.m.s, would be I naught by under root. So when I say root mean square of current or voltage, what does it mean? What does that value tell you? If you look at this graph, the graph of squared of voltage, are we going to a negative value? We are not, right? There is no negative value in this graph. Alternating current was defined as a current that changes direction. So if it goes positive initially, and then it goes negative, and then positive and negative, positive and negative. In this case, when you take the square of such a graph, you just get positive values. So it just means that when I compute the root mean square value of the voltage or current, it is just the value of the direct current that would convert energy at the same rate in any circuit, right? In a resistor, for example. So did that make sense?
Sir, why did we use it in the under root?
Why did we square root it?
Yes.
Oh, because we want, unless you square root it, what value you're getting is for V naught squared, right? You want the value for just V, right? You want your, what do you call this thing? The dimensions to be just for potential. It's, if you're calculating voltage, right? Voltage. So you take the square root of V naught square to get voltage, and then you just give it a new name, root mean square voltage, right? So it is just a value of voltage, a value of current, and that value of current, it corresponds to the direct current that would convert the energy at the same rate in a resistor as an alternating circuit. So if you have an alternating circuit or alternating current, you can calculate from that alternating current the RMS value of current or voltage, and then you can use that value in a direct current circuit. And if you use that value, that means that the direct current circuit will be converting energy at the same rate as alternating current circuit would be doing. So it's kind of a link between the two. So is that clear?
Yes, sir.
Okay. So actually, let me write it down as well. Value of direct current DC that would convert rate as an alternating current. Okay, so we have talked about power and sorry, not power. We have talked about what do you call this thing? Voltage and current. Now there we can talk about power as well. Power dissipated, the power that is lost if I have an alternating current circuit, right? What would be the loss in power for that type of a circuit? So let's discuss power loss in AC. Okay, so what would you expect for this power loss? Because current is changing, right? Current keeps changing. It oscillates between multiple two values, right? And it takes all the value in those two values as time progresses forward. So you would naturally then expect power loss or the power dissipated in the alternating current to be continuously changing as well, right? Because we know that, so let me write it down, that power would be continuously changing as the current okay, so we know that P is equal to I times V, right? And if I consider an AC supply like this connected to a resistor R, I want to see what would be the power loss in this resistor from this by this alternating current. We know that a power loss in resistors is given by I squared R, which is which we get from substituting V equals IR in this equation. Which means, if you remember, recall, I was what? I was I naught sine omega t. So the power loss is also a sinusoidal function. In fact, it is a sine squared function. So it becomes I naught squared R sine squared omega t. Which means that the power loss in this resistor is always a positive value. Even when the current becomes negative, power loss is a positive value. Okay, any questions?
Sir, why are you squaring sine?
Yeah. Oh, because this is I is equal to I naught sine omega t, right? And in this equation, it is I squared. So whatever I have
Yes,
here
got
as
it.
I'll just square it. Okay. sine squared. Okay. Any other questions?
No, sir.
Okay. Okay. So one last thing about